Hey everybody, welcome back. My name is Jacob and welcome to the first video in this series about how to build a blockchain in Rust. It's pretty basic implementation, something that more like looks like a semblance of a cryptocurrency based on a blockchain, but how to build a blockchain in Rust. This video is going to have a relatively long intro to concepts like hashing and Rust and stuff like that. So I will put timestamps in the description or comment below, and you'll be able to skip around to where you want in the video. All right, first off, I do have 4 quick things I want to say about this. First, these videos are based off of a workshop series that I gave at my university this past semester. Second, I'm planning to get to at least these 3 additional concepts on top of blocks and hashing. Those 3 are mining, transactions, and smart contracts. Third, for those of you who aren't really familiar with Rust, I will be explaining a little bit of it along the way, but as long as you've either done some programming in a lower level language, like more systems programming like in C or C++, or if you've done programming in a language that has a relatively strict type system, something like Java, something that has at least stricter than JavaScript, you should probably be good. And then the last thing is you'll notice I'm using Windows. That's because my Linux machine currently has hardware problems and I haven't gotten them fixed yet. All right, so if you would like to code along with this video, please go and download and install the Rust language software development tools. If you're on Windows, you have to install some Visual Studio stuff that can take a while as well. So you might want to get that started now. And also you might want to install Git because I do have a little bit of boilerplate code, but you can also just download that from GitHub too. All right, so blockchains for programmers. When you hear about a blockchain, basically everybody thinks, oh, cryptocurrency, Bitcoin, magic internet money. And well, I mean, yes, cryptocurrencies are really cool, and I could go on a whole spiel about that, but I'm not. We're just focusing on blockchains here. And eventually we'll get to the point where this project will look a little bit like a functional cryptocurrency, but not quite, because that is quite a task for one person to undertake. This is just going to show you the basics of how blockchains actually work. You know, how it's like a state changes and all that stuff. We'll get into that later. But for now, the only 2 things we need to worry about are the blocks and our blockchain. It's basically going to be like a linked list or an array of just blocks that contain information about a block, and they're all in a list. They're all in an array, right? And then in future videos, we'll get into transactions on the blocks, and we don't have to worry about wallets, addresses, balances, peers, networking, nothing like that. And so generic blockchains, that's all we're going to be looking at in this video. In fact, we're just going to be looking at the block, not even the blockchain. So I have come up with 6 basic attributes that we'll be using, that will define on our block. Those will be an index, where it is in the list, a payload. This will be relevant information, data that the block is carrying with it later. This will be transactions, but for now it's just going to be a string, so we can be like, hey, look, a block that has information in it. It'll have a timestamp, so our blockchain has a sense of time. We'll have a nonce. We'll get into that later when we look at mining, not in this video. Previous block hash, that's so that we can verify, well, this block says it's here in the list, but that doesn't match like the other blocks I have in the list, so this block must be bad, right? So a little bit of cryptography going on there, and then a hash that represents the hash for this block and all the information in this block that we're looking at. Sweet. So let's go over this concept called hashing. If you're familiar with it, feel free to skip over this part of the video. Basically, we have a couple of algorithms that are predefined. They're pretty well defined, and these 3 most people probably have heard of. You have MD5, SHA1, by the way, that's Message Digest 5, and Secure Hash Algorithm 1 and 256. I believe MD5 and SHA1 are both no longer considered secure, but they're still pretty popular. Hint, hint, don't use them in new projects. And then I think SHA1 256 or SHA 256 is still considered relatively secure, so that's what we're going to be using in this video. That's a 256 bits it generates, so 32 bytes. And a hash is just you take all of the bytes in your data, so MD5 would take all of the bytes that represent the string GeekLaunch and do all kinds of wacky mathematical things on them that I don't understand because I haven't studied cryptography in depth. And it gives you this guy. Ideally, it will be unique and you will never find a collision meaning two distinct pieces of data which, when run through the hash algorithm, generate the same hash. Ideally, that would never happen, and it is very, very, very difficult to get it to happen. And when someone says that a hash algorithm isn't considered secure, it probably means that there is a way to figure out that there's a way to like generate data that will generate a particular hash or something like that, and that would be a security vulnerability, because the idea is that the only way you can calculate this unique hash is just by running through the steps in the algorithm. All right, sweet. So those are just like fingerprints for data. And okay, let's get into what we will be using. We're going to be using the programming language Rust. And it's like, why Rust? Why not use a programming language that everybody knows and has already heard of and stuff? And it's a couple reasons. First and foremost, I wanted to learn Rust. So I taught myself Rust. I read this book that I have linked on the screen. It's a great book, gives you a great overview of the language. I would highly recommend reading it, especially when we get into more complicated aspects of programming Rust. So that's one reason. And another is that, well, I kind of describe it on this slide. If you look over here, it says pointers are always safe. They're called references in Rust, but pointers, if you're familiar with like the C, like what they're called in C or C++. Pointers are always safe. Basically, you'll never have pointer to null or something like that. You'll never be trying to like clear memory twice or something like that, because the Rust compiler, like the rules of the language, actually make it so that you can't have those errors in your code. So I've come up with like three. These are, now keep in mind, these are like super, super dumbed down descriptions. There's three words that describe each of these languages here. I picked Java because it's kind of, it's lower level than JavaScript at least, and a lot of people know Java. So it requires a virtual machine, which is a little bit of overhead. That makes it slow. It's safe because it has, a pretty good type system, and you're not going to have, you'll get null pointer exceptions, but at least you're not going to totally break huge amounts of things with Java. Sometimes the compiler errors aren't very friendly, but that's beside the point, getting off topic. And it's simple, so the learning curve isn't too difficult. And then I put simple for C. Obviously, you can do complex things with C. Like I said, these are just like super, super, super general. But it's unsafe in that you can make a lot of dumb mistakes in C, and the compiler won't tell you about it. It'll just say, okay, I'll let you, dereference some pointer that is obviously invalid or something like that. And then it's fast because it does not have a lot of overhead, whereas Java has a lot of overhead. It has the virtual machine and the standard library and all that stuff. It's complicated. Rust is interoperable with C/C++. It operates at the same level, and the code, from what I've seen, you can get them to interact with each other pretty easily. It has a friendly, intelligent compiler that plays into this safe right here, in that the compiler won't let you do wrong things the vast majority of the time. And that is also partly thanks to its great type system. It is complex though, so that's why I recommended reading the book, because it's a little bit of a learning curve there, and it's fast because it's interoperable with C and C++. It's not super heavyweight. All right, enough with that. Let's get looking at some code. So I'm assuming most people here are probably familiar at least with what Java code looks like. I also have a JavaScript example, but a Java code example for like what a block implementation using the attributes that I described in a previous slide would look like is probably something like this. You'd have an integer index, a long timestamp, and the block hashes, right? This and string payload, right? And then you'd have, here's your constructor, and then it just assigns everything, right? Here's a block hash, which maybe contains, I think this is 16 zeros or something. So if we were using MD5, basically I just didn't want to type out any more zeros and it would go across the screen and make a big mess and all that stuff. So let's look at approximately the equivalent, I'm doing air quotes, the equivalent Rust code. Obviously it's not equivalent because it's completely different level and language, but in Rust, just kind of more like, if you were in like C or C++ world, well, C world, I guess, we have structs. So it's a little bit like an object, except, so if you're thinking about Java or JavaScript, it's a little bit like an object. It's just all of these guys, so they can either be references or scalar values like this, but they have to be like definitively sized, and all kinds of other things. Basically, it's like an object that can't have methods, like, but it sort of can, because you can implement functions on a struct. So this new function, if you're used to most popular object-oriented programming languages, or a lot of them at least, use the word new as a keyword to instantiate a new instance of an object. You don't have to do that in Rust because these are structs and not objects. So this is like Rust's alternative, or Rust's closest equivalent to a constructor. You just have something that takes whatever properties here and returns an instance of that object, or in this case, the struct, because it's not an object, it's a struct. There are a couple interesting things to note here. For those of you who've never seen Rust code before, there is an implied return statement right here. So this right here, not having a semicolon and nothing up here, you could, and it would work the exact same, put the keyword return right before this word block and then a semicolon here, and it would work the exact same. So that's implied return. And then this right here is an array like initializer. It's kind of this is shorthand for writing a 16 element long array of zeros, and Rust's type system is strong enough to know that so block hash here is an alias for this guy. If this was real code, I would have put that somewhere else, like up here or something, but block hash is the same as this guy right here, same type, it's just an alias. And so a hash is type block hash, and so Rust knows that those have to be unsigned 8-bit integers and not like unsigned 64-bit integers or signed 64-bit integers, because Rust can do that type inference for you. It's pretty smart. And then here's my JavaScript code example. It's the shortest, but also JavaScript is super high level. You'd have to either run it in a browser or on Node.js, and that's just messy, and I wanted to use Rust, so we're not using JavaScript for this project. Okay, so let's get coding. You can download the code, just a little bit of this baseline starter code that I wrote for this project from the GeekLaunch /blockchain-rust repository on GitHub, and then look at the start-here tag, and that'll give you the exact same code as I have right here. All right, so now we're into actually writing code. So let's take a look at these three files that I have here, the three source files that I have here. First is our main.rs file. I'm guessing you can probably figure out what that does. Here's our main function. This is where execution starts. It says print line hello blockchain. What do you think will happen if we run this? It'll probably print hello blockchain. So let's check that. You can run your Rust program by typing in cargo run. Press enter. And it says hello blockchain. Perfect. So that was readable enough. Our next file is lib.rs. This just contains a couple functions. This is where the vast majority of the boilerplate code that I gave you is. It just has a now function, U32, U64, and U28 bytes. Those just give you byte arrays. See, these are U8, so an 8-bit unsigned integer array that is 4 elements long, that's 8 elements long, that is 16 elements long. If you take a look at these, we're just shifting over and then taking them as bytes. Pretty straightforward. Little endian, by the way. And then the now function just gives you the current time in milliseconds. So pretty standard stuff. And let's look at our last file. So this is where we're going to be doing the majority of the work today in this video. We have to implement the stuff in our struct. We'll get into what this is later. And then here's an empty implementation block for our block struct. All right, so let's actually write some code. We're going to start here in our block struct and define some of these properties that we talked about before. So first we're going to have pub index. That's going to be an unsigned 32-bit integer, and that's the index. Where does this lie in the blockchain? Next we have a timestamp. So pub, that's public, by the way, timestamp. And that's going to be an unsigned 128-bit integer, because this function, we'll use this later, returns an unsigned 128-bit integer. Sweet. Okay, so there's our timestamp. Then we'll have a pub hash. That'll be of type block hash. And I define that type right here. Well, it's just a type alias, really, right here. But we do need to import it from this lib.rs file, and this is kind of a special file. You'll learn more about it if you read the Rust book. This is a kind of a special file, lib.rs. We can import stuff from it by this statement here, use super : and then star. That'll import everything because we'll be using these functions later, so we'll just import everything for now. So we have hash, then we also are going to have previous block hash, just like that, referencing the hash of the previous block. Then we'll have nonce, pub nonce, an unsigned, I guess we'll make it a 64-bit integer, and pub, what was the last one? Payload, and that's a string. Now, a seasoned Rustation would realize that I'm using string here just because I don't want to deal with references right now while I'm explaining all kinds of other things that have to do with Rust code. So we might change that later, we might not. Well, actually we will change this later to be transactions instead of a string. We'll just leave it as a string for now. Don't kill me. Don't shoot me for it. Okay. Like I said, we'll ignore this for now. And yeah, so these are all the properties that we need in our block struct. So great, it doesn't actually do anything. This is just describing our data structure. So might as well write a constructor to get used to writing a little bit of Rust code. So what I'm going to say here is pub fn, that's public function called new. By the way, IMPL stands for like implementer, implementation, and then we're implementing functions that correspond to block, the struct. So public function new, and then we'll have a list of arguments that looks very similar to this. So I'll just copy paste it in here. Indent that a little bit. Whoops, I don't need that. And we can delete these guys like this. And whoops, sweet. Okay, so we don't want hash in there, but all the rest of these can stay as arguments. And then this will return, this is how you indicate the return type, self. And self just means block in this case. So if you remember from that slide, we can use the implicit return here because this is a pretty simple function that just instantiates a block with a couple of defaults. So we'll say block like this. And like I said, this is just like saying return like that. Same deal, just a little more concise, a little cleaner, less stuff to write. So we can take these guys, paste them in there. indent them up a couple times, delete these. And just like in JavaScript, we can, for the most part, delete these guys. Hash, we'll make that a vector, because if you remember, this is a vector of bytes unsigned 8-bit integers, and we can use just like we can for arrays, we can use the same initializer syntax. So we'll just make it all zeros. It'll be 32 bits long because we'll be using the SHA 256 hashing algorithm, and that is 256 bits, which is 32 bytes. Previous block hash, we're getting that as a parameter. Sweet. Nonce. Sweet. Payload. Sweet. Done. Hopefully. Please work. Yes. Okay. Sweet. Now we have a constructor, but it still doesn't really do anything. So before we test it, we're going to write out one more function here. And that's this implement debug for block. Now, usually you can derive debug, and that's probably this is for people who know what Rust is. Usually you can derive debug, and that's probably a better idea than what I'm about to do here, but I do want to illustrate how to use some of the string interpolation features of Rust, so just deal with it. This is not production level code. Okay, so basically we'll be able to print out a block in a line that looks similar to this, but we need to say, what does this look like when it is printed? So right now all of the blocks will just say block, and we need to give it some more details. So I'm going to put in square brackets the index. Obviously, this is just a string in here. So we can use some string interpolation here. Curly brackets, curly braces, we will fill those up in just a bit. So this is just kind of like a template for what it'll look like. So a block with a hash, we'll put the hash right there. So we have the index, the hash, we'll say @ colon, and then the timestamp, we'll say with, and then we'll put the payload data. Then we'll put a comma here, and over here we can fill in these empty spaces. So the first one is index, so we'll say self.index, and then the next one is hash, so we'll say self.hash. That'll be all zeros for fresh ones that we haven't done anything to yet. And then we'll have the timestamp, so self.timestamp, and then with self.payload. Okay, this will actually give us an error in just a sec. There we go. It says this vector doesn't implement display. So I could use the debug output, but I'm not going to. Instead, I want to display this using easier to read hexadecimal notation, because this would otherwise just look like an array of numbers, which, not that hexadecimal notation is necessarily easy to read, but it'll look a little nicer. And I don't want to write my own hexadecimal, like change to hex function, so we're going to grab somebody else's. That's right here, this hex package. They're called crates when you are talking about Rust specific stuff. You can get it. Their entire repository of public crates is at crates.io. We're going to use the hex crate. It's pretty popular. All you need to do is copy this guy right here, come back over here, go out to your cargo.toml file. Is that toml? I don't know if that's how you pronounce it. Paste it in there under dependencies, and right. Okay, so now we can use the hex crate, and all that I want to do here, you could read the documentation, but I know this crate, so it's hex : encode, and then a reference, and there we go. That should work. All right, so let's actually test this out. Let's go over to our main function. We can delete this, and let's create a new block. So let's say let block equals block : new. Now there's actually a problem here. we can't access that guy because it said failed to resolve undeclared type or module. So we have to actually get that from our library here. If you look at our cargo.toml file, we have a library defined in the project and a binary. And the library is called blockchain lib. So let's use blockchain lib : star. That's just everything because I'm lazy. Now we can use block new, and that'll take an index and then a timestamp. I'm just setting them all to 0 for now. We'll set it like to now or whatever later. So let's see, it's an index timestamp. Previous block hash will be a vector, and we'll just use zeros and give it 32 of them. The nonce we'll leave at 0, and then here's our string payload. That's the data that goes along with our block. We'll say Genesis block.to owned, because of how strings work in Rust, it's a little bit complicated to explain, but that's what I was going on about a little bit when we typed in this here. But to owned, sweet. And now let's print out our block and see what it looks like. So print line, okay, and then it gives us this guy. This would actually print out if this said display, but we want the debug one, so we do : to get the debug one. I'll say ampersand, it's a reference, block. Okay, so hopefully this works, and let's run it and see what we get. Sweet. Okay, so this is the hexadecimal representation of 32 zeros, I guess. How exciting. It's a block at index 0. We can check that if we said like block at index 13 at timestamp 1, 2, 3, 4, 5. All right, let's say now. Previous block hash, nonce, we didn't change, and Genesis block, exclamation point. We can see that all of those change. Beautiful. Okay, so this is all well and good, but it really doesn't have, it's just holding information. Let's make it interesting by hashing the information that is inside. So we could implement another function, pub fn hash, and that would give us the hash. But what I want to do is, because we'll be hashing other parts of our blockchain later, let's actually implement, or let's create a trait called hashable in a new file. And now a trait is a little bit, you can probably think of it for now kind of like an interface, if you're familiar with interfaces in like Java. It's a little bit like an interface. So we'll say public trait hashable. We put stuff in here. We'll have two functions in here. One that we will define a body to, and one that we won't. The one that we will define a body to is the actual hash function, but it will take a vector of bytes that need to be hashed. And so we'll define another function called bytes that will just give us the bytes for whatever struct this is implemented on, and those bytes that the function will deliver to us are the ones that need to be hashed. So we'll say fn bytes. That'll take self. So it's kind of like, so it can use this. If you're familiar with Java or JavaScript, self is a little bit like this object. If you hadn't picked that up when we were doing this here, self is a little bit like this. So self will reference the current, I suppose you could call it the instance of the struct, and it will give to us a return value, a vector of bytes like this. But we're not going to define a body to that, so we'll just put a semicolon there. That's for someone else to define on whatever needs to be hashable. Then here's the one we will define, function hash self, and that'll return a block hash. Well, actually, since this won't be specific to blocks, let's say vector u8 like this, and then we'll have stuff in here. So that'll be a hash. So I don't want to implement a hash function because I'm not a good enough programmer to do that. Implement my own custom hash function, let alone who knows if I could even understand the SHA 256 code. I've never looked at it, the actual algorithm specification. So we're going to have someone else's implementation do it for us, and we're going to use this crate, the crypto-hash crate. So we'll copy that, move that over to our project configuration file, our TOML file. I don't know if that's how you say it. And now we can use the crypto hash stuff. So like I said, look at the documentation. This is just what we need here. Crypto hash digest. And remember, this will be like an implicit return. So then we say crypto hash, and we need to specify the algorithm. And that one will be SHA 256. And then the data that needs to be hashed, and that will just be self.bytes. And we know that we have the bytes function because it's right here. We just don't have a body for it because this is a trait. All right, so there is our hashable trait. Sweet. Let's implement this bytes function on our block struct. So we actually need to create a new IMPL implementation block. So we'll say IMPL hashable for block. Okay, so there will be an error here. Just a sec. Okay, hashable, cannot find trait hashable. That's because it doesn't know where it is. We need to, I'll just put it in here so it gets imported. Hashable with, there we go. So it gets imported with this statement here. So now it should be fine. Now we're implementing it wrong because we don't have the bytes function. So we'll say fn bytes, and then takes self and returns a vector of bytes. All right, so now how do we get the bytes out of the relevant information here? Well, this is where these functions are going to come in handy. U32, 64, 128 bytes. They're going to be useful here. So let's define a variable, let bytes equal a new vector. Looks like this, and then we'll use our implicit return to say bytes right here, and we'll return bytes. So this will work. It'll just be an empty vector of bytes. Very boring. It'll give us the same hash for everything. So we need to put all of this information in there, except of course for this, because that's what we're calculating. This is the fingerprint, and everything except for this property is what needs to be fingerprinted. So we'll do that by calling this function bytes.extend, and that'll just add kind of like onto the end of the vector. So extend with what? So we'll start with index, and that'll be u32 bytes self.index, like so. Now we will get an error here in just a sec. Sorry, my computer's a little slow. It says cannot borrow bytes as mutable, as it is not declared as mutable. So here's an interesting thing about Rust, is that everything is immutable by default. We can change that by just saying mut right there. Let mut means mutable. Let mutable bytes equals vector. Now we can change it, and that's significant because it means that your variables are only going to change when you specifically say, yes, this one is allowed to change, as opposed to having to declare everything as a constant, and sometimes that can get messy. So just everything is immutable by default, but now it's not, so we can change it. Sweet. So let's add on our timestamp bytes. So this will look really similar. We'll just use the 128 bytes function here, and this will be timestamp. Sweet. The next one for previous block hash is a little bit different and interesting. So right here, we'll just reference self dot, what is it called? Previous block hash. And it'll just extend it right away for us. Pretty simple. Then our nonce, that'll be similar to this guy, except our nonce, I believe, is 64 bits. Here, nonce, okay. And then lastly, our payload, which is a string. So it looks like this: self.payload as bytes, and that will actually return a reference for us, so we don't have to create one using the ampersand like that. And there we go. Those are all of the relevant bytes in a block that need to be hashed. So now let's test this guy out and see what it looks like. So I'm going to say let hash equal, or just let h equal block.hash. That'll generate the hash, and then say print line. It looks like this. And since this guy will be a vector of bytes, as you can see there, a vector of unsigned 8-bit integers, just bytes. It doesn't actually have one of these guys implemented. If I said h, it doesn't have a display implemented, but we can use the debug formatter to display it. So let's run this code and see what the hash of our block looks like. So it's just this list of numbers, 201, 99, 9, 251. Beautiful. If we run this again, we should get the exact same thing. 201, 99, 9. But if I change this nonce just to 1, we're flipping literally like 1 bit, and run it, now it's completely different. There's very little, if any, there's probably like no similarities at all. I mean, except for it's 32 numbers in a list. But yeah, that's because of an effect called, I believe it's called avalanching in good hash algorithms. And so now if we do this again, we'll get the same 201, 99, 9. And it's just so that you can't say, oh look, the hash is close, so the data must be close. Yeah, all right, so there we go. We have implemented the hash function. Sweet. Last thing to do is just set it as part of our block. But remember, our block is currently immutable, so we have to make it mutable. So we'll just say block.hash equals h. We can do that. Sweet. And then let's print out our block again and see what's going on in there. All right, and there we go. There's our beautiful hex encoded output here of our hash, C963. And if we change Genesis block to Genesis block exclamation point or something like that, now the hash is totally different. 8563 C9063 again. Interesting. But you wouldn't really be able to tell. Those would be the rest. I mean, it's completely different outside of that. That's interesting. All right. Well, there you go. That is a basic introduction to Rust programming, and this will be the basis for more blockchain videos going forwards. I hope you enjoyed this video. I hope you learned a lot. I really like programming in Rust, and this is a really fun project that we're doing here. Eventually, this project will, with a lot of help, it will look a little bit like an actually barely functional cryptocurrency with smart contracts, which is fun. But yeah, I really enjoyed this video. I hope you did as well, and I will see you in the next video. Have a good one.